The key idea of this paper is that we aim to leverage NeRF for 3D object detection, but we do not want to the person optimizations.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper NeRF-Det, Learning Geometry-Aware Volumetric Representation for Multi-View 3D Object Detection. This paper was published in ICCV 2023, and I am happy to host the first author of the paper, Chenfeng Xu. Hello and welcome to the podcast. Can you introduce yourself?
Hi everyone. I'm Chenfeng Xu, and I'm currently the third-year PhD student at UC Berkeley. And my research area is about 3D vision, especially to build efficient 3D representations for the applications like autonomous driving, robotics, and AR/VR. And my advisor is Masayoshi Tozuka and Kurt Kuzer. So if you have anything want to collaborate with me, just call me. Yeah.
And who are the co-authors of this paper?
Yeah, the cause of this paper is Bicheng Wu. He is the research scientist in Meta, and Houji, Sam Cai. They are also the scientists in the Meta. And Ray Long Li, he's my colleague in UC Berkeley, and he is also the author of NeRF-ACC. So he's a very awesome guy. And Zha Liao Wang is also the research scientist in Meta. And Wei Zhan, Kurt Kuzer, and Masayoshi Tozuka are the research faculty in UC Berkeley, and Zijian He and Peter Rada are in Meta Reality Lab. So these are the co-authors.
All right, let's get started. So in the TLDR kind of format, 2-3 sentences, what is this paper about?
Yeah, so this paper is about, in this paper we propose NeRF-Det. We aim to achieve indoor 3D detection from purely RGB images. And actually in our paper, we leverage the advantage of NeRF to learn good geometry for 3D detection. So while we want to eliminating the needs of heavy overhead of person optimization in NeRF. So this is the main scope of our paper. And by this way, we can achieve state-of-the-art on the 3D object detection, and we can achieve non-trivial depth estimation and low-view synthesis.
Okay, super exciting and interesting. I can't wait to dive in deeper. But before we do, let's do a short intro. So what problem exactly is this paper addressing?
Yeah, the problem of this paper addressing is the 3D detection from purely post-RGB images. Actually, in current mobile devices such as mobile phone and AR/VR headsets, there's no any depth measurements. So it's really hard to get 3D objects in a 3D space. So we want to detect objects in 3D space from purely cameras are very important. This is especially useful in like AR/VR devices and mobile robotics and mobile phones. So for in these applications. And in this paper, we hope to develop the state-of-the-art methods for 3D detection from only image as inputs.
Right. And what are the main challenges here?
Yeah, actually, the main challenge here is that to estimate the 3D geometries from pure images, where we want to get state-of-the-art 3D detection. Since 3D detection lies at two challenges. The first challenge is estimate 3D geometry, and the second challenge is to understand the semantics and get the bounding box. So these are the key challenges in this paper.
Right. So if I try to break it down and put it into my own words, right? Your input to your method is like a stream of images, right? Captured from some device.
Yes.
And the output that you want to get from this is twofold, right? You have two outputs. One output is the detection, right? So detection is a bounding box around the different 3D objects. But since these are 2D images, you first have to get an understanding of the geometry, or kind of like what is the 3D scene around it. And then you get the bounding boxes with the classes of each object within it, right?
Yes.
All right. So what is the main contribution of this paper then?
Yeah, so the main contribution of this paper is that we are very different from previous works that explicitly estimate the depths or try to directly build the NeRF and then get the 3D geometry and then detection. So in our paper, our key contribution is that we leverage NeRF in an end-to-end manner. So we do not need any personal optimization for NeRF, while we can leverage the advantage of NeRF for learning very good geometry, and we use it for detection. So this is very efficient, and we can get a very good performance for 3D detection by leveraging the advantage of NeRF. Yeah.
Right, super interesting. So what you're saying is a lot of like some of the previous method kind of did the NeRF side, so figuring out the geometry as a first step, and then as a second step, completely separate, they do the detection, right? What you're saying, like what's your main contribution is, you're saying, oh, let's bring those two branches together and train them simultaneously, and that way they can inform each other and do a better job at detection.
Yeah.
Really nice. Okay. But before we dive into the method, let's talk a little bit about related work. So which one or two papers should people read before reading your paper?
Yeah. So before, I think here, not only one or two. So to let the audience better understand our work, I want to first introduce from the very vanilla method for addressing this problem. So as we want to address the 3D detection from purely RGB images. So the most straightforward way is directly estimate the depth from single image. For example, if you want to detect 3D objects if you want to detect objects from an image, we want to know depth. So, however, if we directly estimate depth from single image, this is very inaccurate. For example, the most famous work is MIDAS. So this is a single image depth estimation works. And we applied it on our network. We find that depth is very inconsistent. For example, for the same object captured by the one thing and captured by one image, and if we detect it on this image, the depth is inconsistent from the other image. So we do not want this. And a better way is to leverage the multi-view image depth estimation. This can make sure the depths are consistent. However, this kind of methods would suffer from the occlusion and the transparent object. So we also do not want this. And the most related work of our paper is the image voxel net. The image voxel net is really a great work that it tries to implicitly to model the scene geometry. For example, given a series of post image, we can assume that the room, since we target at indoor 3D object detection, so we can assume that the room is built from a cube volumetric. And for different image, we can shoot a ray based on this pose, and we can scatter the features on the rays. So for each voxel in the volume, if there are several rays that's across on the same voxel, they would average these features, and then they would build a very good volumetric features for 3D object detection. However, the key issue of this kind of method is that since we do not know the depth of each pixel, so we do not know where the feature should put on the ray. So in their method, they just directly put the feature on each point of the ray. This would make the scene geometry very ambiguous. And we also do not want this. So here, and we try to leverage the NeRF to eliminate this scene geometry ambiguity. So for NeRF, actually, I think most of people have heard of NeRF. NeRF is cutting-edge scene geometry reconstruction work. I would summarize it into two parts. The first part is mapping part, and the second part is volumetric rendering parts. For the mapping part, they try to map the different locations and the view directions to the RGB and the density. And the density can describe the geometry. And the second part is volumetric rendering. We can directly render depth or the RGB from the density and color it estimates. So our paper especially leverages the property of NeRF that gets estimates density that describes the geometry from volumetric rendering. So this is the related work and the key contribution of why our key contribution comes from this related work.
Yeah, these are all super relevant and interesting papers. I'll make sure to put a link in the episode description so people can do a full read. So, okay, now let's talk about your approach. Okay, so tell us, how did you do it, right? You've got your input, you've got your stream of images. What do you do?
Yes. So in our paper, so what we do is that we try to connect the advantage of NeRF for learning geometry for 3D detection. So what we do is first we collect a series. So our input is a collect of images, and we input into image backbone, and we can get the image features. And then we try to build a geometry-aware volumetric representations. So we follow the previous image work set. We first build a geometry ambiguous volumetric. So basically what we do is that also based on this camera pose, we scatter the features on the array and we average them into volumetric cubes. And however, this kind of feature grid is very ambiguous. So what we try to do is connect another NeRF branch to better get the geometry-aware volumetric representations. So we have another branch. So in another NeRF branch, we collect. So basically, we try to estimate. We try to leverage the volumetric representations. Basically, we choose a novel view as the input, and we shoot array, and we shoot the novel array and we sample the points on the 3D positions, and then we project the feature. We sample we project points onto the different point view features, and we get this feature, and we input them into a GMLP. In this GMLP, the main work of the GMLP is to estimate the density, and then we would use the output of density and hidden feature, and we input into the color MLP to get the color. And finally, we would use the volumetric rendering to estimate the color and depth, and the photometric loss and the optional depth loss can help to optimize the GMLP and color MLP. And so then we try to connect these two branches. Since the NeRF has already optimized a good GMLP that estimated the geometry, we want to use it for optimize the very ambiguous geometry volumetric representation in NeRF in detection branch. So therefore, we directly use GMLP to estimate the density for the volumetric representations of the detection branch, and we can get the opacity grades. We multiply the ambiguous geometry grades and the opacity grade together in detection branch. The effect of this branch is that it can eliminate the empty space of the volumetrics in the detection branch, such that we can get better detection results. So this is our approach.
Okay, wait, this was a bit much. Let me try to recap and tell me if there's something I'm not getting right, okay? So you take your input images, you feed them into a backbone to get features, right?
Yes.
Now, those features are like they exist in this volumetric space, right? So for every 3D point in this voxelite space, you have a feature that's associated with it.
Yes.
Now, then you take those features and some positional encoding and you feed it to this GMLP, which is shared with the NeRF branch, right? And on the NeRF branch, you're getting the image, but now what you want to actually do is get the densities, right?
Yes.
Now, once you fed that in and you got the densities, you can now basically element-wise multiply the densities and the volumetric feature grid. And now you know which features are basically you're disambiguating this like ambiguous feature space, right?
Yes.
And on the NeRF branch, you can now like just continue as usual to get the color at every pixel and train it with a kind of reconstruction kind of loss.
Right? Yes. The whole network are end-to-end training, so such that the NeRF loss can optimize the GMLP to help the detections.
Right. So basically the shared part here is the GMLP, right? This is the point. This is the module that kind of connects between the detection part and the NeRF part, right? Because after you got the densities and you got the features, you feed that into a detection head and that gives you the detections, right? Yes. Now, but how do you train this, right? So what are the loss functions? So what do you optimize?
Yeah, the loss function of this method is that we have two kinds of loss. The first loss is about the detection loss. We have the very traditional detection loss, less localizations, semantic labels. And for the NeRF branch, we use the RGB photometric loss. And if we have depth measurement, since sometimes we can't get the depth measurement. So if we have depth measurement, so we can use depth as the supervision to get depth loss. So yeah.
Right. So you're basically optimizing it to solve both problems, right? So the photometric loss is to get a good novel view, and the detection loss is to get a good detection, right?
Yes. Yeah, and I want to highlight that during inference, we do not lead the NeRF branch. We just keep the detection branch, since we have already trained a very good GMLP. So the GMLP can help the detection branch get very accurate geometry-aware volumetric representation. So that means that we can just keep detection branch. We do not introduce a lot of extra overhead for the detection.
Right, because like when I first started reading the paper, I was thinking, well, with NeRFs, you always have to go through every new scene that you take the images, you train the NeRF, it takes a while, and now to put detection on top of that. But this is not the case here, right? You're basically training it on one set of data, right? And you solve the NeRF and you solve the detection. But then at test time, you don't need the NeRF part anymore, right? You just feed through the detection.
Yes.
This is really cool.
Yes. Thank you.
Okay, great. So let's move on to talk a little bit about the results, right? So how do you evaluate this kind of method?
Yeah, we evaluate this method on two datasets. The first dataset is ScanNet. So this is the very well-known indoor 3D detection dataset. And the second dataset is ARQ-Things. This is from Apple, and it's kind of a new dataset relative to the ScanNet. So we evaluate the detection results on these two datasets, and our main baseline is, as I said, is ImageVoxNet. In ImageVoxNet, it's try to scatter the directly scatter the features on all the positions of the ray. So this means that their geometry is very ambiguous. So we just additionally introduce a NeRF branch, and this NeRF branch do not introduce any extra labels. We just use pure RGB as the label. So we do not have any extra labels such as the on box label or something. So we can get significant performance improvement on both ScanNet and ARQ-Things. So we test it on different backbones. We test it on different settings. For example, with depth estimation and without depth, with depth supervision and without depth supervision. So both these settings demonstrate that by additionally introduce a NeRF branch, the detection performance can be improved a lot.
Excellent. But when does it fail?
When does it fail? Good question. So we find that we can say it fails. We can say that it performs not well as the others. For example, in the sparse view. So, for example, when we collect the images, so if the image is very sparse, the image set is very sparse in a scene, we find that the performance is not as good as the dense views, but it can still perform better than ImageVoxNet, but it's not what we expect. This makes sense since I think in NeRF, for current NeRF, they are suffer from the sparse view. So NeRF needs the dense view to reconstruct the 3D things. So we also suffer from these issues. So we maybe we can solve this in the future work.
Yeah, because there are some methods that kind of solve this in NeRF in very different ways, but basically it would be to integrate these methods into your NeRF pipeline, and that would potentially improve the detection side as well. Yes, that's true. Were there any kind of surprising or unexpected results?
Yeah, I think there are some surprising results. So what the experiments I really like is that actually this also reviews such as what we do. So actually here's another trend of work that's first train NeRF and then use the estimated geometry, for example, like density or point cloud to as an input and apply the point cloud or 3D convolution to then detection. So the very classic work is called NeRF-RPN. So in their work, you first train the NeRF and then get the point cloud and then apply 3D convolution for 3D detection. The review asked us to compare with it. Surprisingly, that our work is another trend. we joint train nerve and detection together. So multi-view consistency loss, this is good for detection, and this helps us to get better detection. Surprisingly, you will find that our method is better than it. So we have two comparison settings. The first comparison is that we train the same data. Since nerve RPN requires to overfit each scene one by one. This so this cannot scale. Since overfit a scene costs a lot of time. So in their work they just overfit several things. So we first compare with them with the same things, and our performance is better than it. And however, I want to highlight that our work can train on a large data set. Since we can just train detection and nerve together, so we can apply it on a large data set. We can train them. However, it's hard for nerve RPN, or we can say that's first nerve then detection kind of method to do this, since they require to overfit scene one by one. It's hard to overfit on large scale things. We find that by training on large scale things, our performance is largely improved. Maybe I can give a number. So in their test sets, they can get only AP like 30 and we can get 60. So this is very surprising. So this is what I really like our method.
Yeah. I like that part too, right? I think this is one of the biggest upsides of this method, right? Is that you don't need to overfit on every new scene, right? So that saves a massive amount of time for any first nerve then detect kind of method, right? Because every time to just overfit to that scene and just then run the detection, these are great works and they're pushing the boundaries of research forward, but in practical kind of aspects, it's like you need something better. You need something that would work kind of like faster in many ways.
Yes.
Yeah.
And I also want to talk about what I feel a little bit frustrating in our work. So that is actually our novel synthesis result is not that good. So yes, if you look at our paper, so our average PSNI can only get like 20. So this is not a high value, high results, high performance for novel synthesis. So, and we also find that additional introduced detection branch is not good for novel synthesis. Novel synthesis, additional adding a novel synthesis branch is good for detection. However, additional adding detection branch is not good for novel synthesis. So this we feel a little bit frustrating, and maybe in the future we also want to improve the novel synthesis results.
Yeah, for me it made sense, right? Because when you added the branch for the detection part, right, you added a loss function that now tries to improve something different than the traditional, photorealistic loss, right? The rendering loss part of it, right? So when you add those losses, you're basically pushing or pulling the solution towards something that's not the best for this task, right? But like to me, it makes sense that if you have more information, it doesn't matter if it's detection or the semantics or whatever, it should help in some way, right? So maybe it's about finding the right loss function or the right architecture to combine these kind of things in order to, maintain the high quality of the novel view synthesis while also getting the detection informed of that and get good performance on both. Excellent future works, right? Which really brings me to the next section of the podcast, right? Conclusions and future work section. So we already have the future work covered. But maybe there's more. So how do you see the impact of the paper going forward?
I think this kind of paper first is open up another path for this kind of trend, this kind of field. So for example, previous works like first estimate depths and use the depths. These depths can be estimated from like a single image depth estimation, like multiple image depth estimation, NeRF first over reconstruction word and then detection. So basically, all of them are first estimated geometry depth and then get detection. But we open up another path that we do it together. So basically, this is more efficient and this more close to what's very popular in NLP, that's so-called multitasks, or we can say that's foundation models. It can do everything. So basically, this paradigm it can be adapted to any of this foundation format. For example, we can add another head, and we can do them together, and we hope that different tasks can help each other. So I think this is a new trend. And second, that I think this can help actually we conduct experiments on only indoor data set, and we hope that in the future work we are exactly doing this. So we hope to extend into the outdoor things. Outdoor things is more complex. It has dynamic objects, and this is not as indoor thing that we can use the volumetric to bounded thing. The outdoor thing is unbounded thing. So we hope to better leverage the unbounded rated loss, unbounded rated NeRF to help the outdoor 3D detection. So this is another future work we are targeting.
Yeah, super interesting and very challenging, right? If you outdoor scenes, add dynamic stuff to it, it's getting complicated, but very interesting and nice future work directions.
Yes.
Okay, so moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments you had in the review process.
Yeah, so I really appreciate that that the reviewers suggest us to compare with the first NeRF, then perception. So I really like this experiment, and I think this comments makes our paper better. And yeah, so I think this is the most valuable comments. And they also suggest us to compare more with other reconstruction then detection related method. For example, first reconstruct the mesh and then compare with and then do detection. So I think this the same track. And the critic in the reviews are many from that we do not conduct. If you look carefully in our table 1, our performance is not as good as directly detect from point cloud. This is a little bit frustrating since our detection results are mainly from the pure images. So we do not have any depth measurement. So we do hope that we can be very close to the point cloud detection. However, we find that we still have a distance to them. For example, the most representative work, VoltNet, they have 58, but we can get 53, 54. So it's very close, but we really want to, we can beat them. However, it's hard. Yeah.
Yeah, I'm a point cloud person, right? So knowing that the results on point clouds is still better is good news for me. But yeah, I agree. I mean, it makes sense to me that at some point in the future, all of the representations would kind of find a way to work together, right? Because you're working only with images. So obviously with images, you don't have the depth. So you don't have exact 3D information that the point cloud has, right? So in order to perform just as well, you kind of need the information to come from somewhere. So sure, there is multi-view. You can get some 3D from multi-view, but it's not as accurate. And it builds up on challenge on top of challenge on top of challenge that you could solve each one individually, but maybe the question is, why should you? If you can get a good quality point cloud, why not use it, right?
Yes.
I guess it's not that easy, right? So if you're talking about handheld or devices or kind of AR, VR, then sure, these are huge power consumption sensors. So maybe there's kind of a more of a hardware constraint than a software one, right?
Yes.
Yeah, really interesting. Yeah, and I think these comments from the reviewer are super insightful and eventually really made the paper better.
Yes, that's true.
Well, maybe I'll add that there is I want to say thank you on behalf of the community for publishing the code and having everything online accessible for everyone to be able to kind of pull it from GitHub and reproduce it and kind of try it themselves. This is really valuable. Yeah. Not everybody takes the time to do it. So kudos on that.
Yeah, thank you.
Okay, so it's time to wrap up.
Yes.
Thank you for being a part of the podcast. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.